All right, welcome. Today, we're diving into something that sounds like it's straight out of science fiction, but it's getting closer and closer to reality. We're talking about a quantum native database, and we're going to break down how this could completely flip the script on how we find information, maybe forever.
So let's start with this classic problem. How do you find one needle in a haystack made of a trillion pieces of straw? This isn't just a fun little saying anymore. It is the central challenge of our digital world. Our data is growing like crazy, and our ability to find the one right thing we need, well, it's getting nearly impossible with the tools we have today.
You see, our current computers have a really simple but really slow strategy. They just check every single piece of straw, one after another. Now, when you're dealing with trillions of pieces of data, that one-by-one method just doesn't cut it. We are slamming right into a fundamental speed limit. And that brings us to what we can call the data search dilemma. It's this growing gap between the super complex questions we need to ask and the insane amount of time it takes for our classical computers to even find an answer. This is the exact moment where quantum computing steps onto the stage.
To really wrap your head around this, imagine this for a second. You have to find one specific sentence, but to find it, you have to read every single book in an entire library, page by page, word by word. That's exactly what a linear scan feels like for a computer searching a huge database. It's just exhausting and so inefficient.
So how in the world do we break through that wall? Well, the answer isn't just a faster computer. It's a completely different way of thinking about computing. It means we have to start thinking in superposition.
Okay, so at the heart of this whole new world is the qubit. A classical bit, it's like a light switch. It's either on or it's off. Simple. But a qubit is more like a spinning coin. While it's spinning, it's not heads and it's not tails. It's kind of in a state of being both at the same time. And this incredible property is what we call superposition.
And the difference here is just profound. A classical bet holds one piece of information at a time. A qubit, because of superposition, can hold and process countless possibilities all at once. It's not just a simple upgrade, it's a whole new language for information.
This leads to a really fascinating outcome. A classical database gives you one solid, definite answer. Here it is. But a quantum database, it gives you something totally different, a wave of probabilities. It doesn't exactly hand you the answer. Instead, it points you with extremely high certainty to the most likely answer.
So how does a quantum computer actually use all this probability stuff to find our needle? Come on, let's peek inside the quantum engine that makes this incredible search possible.
It all runs on a process called Grover's algorithm, and honestly, it's pretty ingenious. First, you load the whole database into superposition, so every single possibility exists at once. Then, this special function called an oracle goes in and essentially tags the right answer. You can think of it like making the needle vibrate at a totally unique frequency. And finally, the amplification step, it's like putting on noise-canceling headphones. It boosts the signal of that one vibrating needle while hushing all the noise from the straw, making the right answer pop right out when you measure it.
And the result of all this? A completely mind-blowing speed-up. A classical search takes n steps, where n is just the number of items. A quantum search, though, takes roughly the square root of n steps. For that trillion-item database we talked about, that's the difference between a trillion operations and just 1 million. It's a total game changer.
But you knew there was a but, right? Of course there's a catch. This incredible power comes with its own set of very unique challenges. This isn't magic, it's physics. And that means we have to balance this amazing potential for speed against the reality of a very noisy environment.
So here's the core challenge. Quantum states are unbelievably fragile. The tiniest little disturbance, what scientists call noise, can completely mess up the calculation. So a quantum database can't just go full throttle for maximum speed all the time. It needs a really smart optimizer to constantly balance that speed against the risk of errors.
The solution, for now, is a hybrid approach, all managed by this incredibly smart optimizer. For every single query, it analyzes the quantum path and asks some really important questions. Okay, how fast is this going to be? What's the real probability of an error? And maybe most importantly, is this actually going to be any better than just using a good old classical computer for this specific task? It's all about dynamically picking the right tool for the job at the right time. To put it really simply, a classical optimizer is just looking for the cheapest, most efficient path from A to B. A quantum optimizer, on the other hand, is more like a master strategist. It's constantly managing this complex trade-off between raw speed, the risk of noise, and the overall probability of success. It's a completely different way of thinking. So where is all of this headed?
Well, the researchers behind this idea have laid out a really clear three-stage roadmap that shows us how we get from where we are today to a truly quantum-native future. Right now, we're in stage 1, what you could call the quantum-assisted era. This is where quantum computers are like these highly specialized assistants, tackling the really tough search problems that get handed off from classical systems. This is the stuff happening in labs today. The next step is quantum-centric, a true hybrid where data just flows seamlessly between classical and quantum memory. That's when businesses might really start to see the first real-world uses. But the final destination, the end game, is stage 3, a quantum-native world, powered by fault-tolerant hardware, where all our data can live and be processed entirely inside the quantum computer. That's the dream.
And that just leaves us with one last really fascinating question to think about. When finding the needle in any haystack, whether it's discovering new drugs, modeling our climate, or understanding financial markets, becomes almost instantaneous, what currently impossible problems will we finally be able to solve?